Hello everyone, welcome. Now what we're going to look at is the voltage drops that would exist in this series circuit based on the parameters that we've already established. My total opposition to 30 ohms, I have 4 amps of current, and I will have a 120 volt source. So Kirchhoff's voltage law stated that he used a few different variations, and there's a few different variations of the wording how it goes, but for myself, I like to keep it simple. I like to look at it as the voltage that exists at the source has to exist within the circuit. So if we have a 120 volt source, if I add up the voltage drops within my circuit, it has to equal 120. Now with a series resistive circuit, it's nice and simple. I can just do the voltage plus the voltage plus the voltage because they're all in phase with one another. If you had different components like a resistor, an inductor, and a capacitor, it still will equal 120 volts, but based on their phase relationship, they may have to be added just a little bit differently, and we'll get into that in some upcoming videos. But for right now, we'll just keep it with resistors to keep this nice and straightforward. So if I have 120 volts and I have a total of 4 amps, what I can do is I can look at the voltage drop at this one resistor by transposing Ohm's law, and it just becomes something as simple as the voltage is equal to the current times the opposition of that component. So we know with the series circuit that the current is 4 amps leaving the source, so that means I have to have 4 amps of current at that point. So now I can look at what the magnitude of the voltage drop based on this one resistor. Okay, so this is there will be 40 volts across. Based on 4 amps times 10 ohms, I would have 40 volts across this one component. So there's a couple of things that we can do. We've looked at how to solve for that one value, but now let's look at the relationship just based on this formula between the other components. So this is 10 ohms, this is 5 ohms. So if we look at just the relationship, not necessarily the numbers this time, let's just look at the relationship. Well, if my opposition is double at this point compared to this point in my circuit, then the voltage drop here has to be double this value. We just write the formula out like this. So if I had an increased opposition, my volt drop must be higher. Okay? In this case, because it's 5 ohms down here, we should actually we'll change that and we'll say, when we're looking at just this value, because my resistive component is lower, my voltage drop must be lower. And I actually know the magnitude. Because the opposition is half, the volt drop has to be half. So I would know, just based on that 40 volts, this has to have 20 volts across it. And I can actually prove it with the numbers now. It is 4 times 5, 20, it is, that's fantastic. That just proves us to the relationship of how the magnitude of the opposition is going to determine the magnitude of the volt drop. So if I come over here, let's look at this a different way again. Kirchhoff's voltage law said my total applied EMF has to exist within this circuit. So the voltage of 1 plus the voltage of 2 plus the voltage of 3, this all has to equal 120 volts. I have 40, we used the calculation, we looked at the relationship, so let's look at Kirchhoff's voltage law to determine what exists here. So my applied EMF is 120 volts, so I have 120 volts is going to equal, let's call this V1, so 40 volts, plus an unknown value here, let's just leave that as V2, plus 20 volts, because we know that value based on the relationship that we already looked at, 20 volts. So all I'm missing is what is that value? So I can transpose this and I would do 120 minus 40 minus 20, and I would have 60 volts is equal to the voltage drop across that component. Now let's do a double check. Did all of these relationships still hold true? Is the voltage drop here equal to the current and its opposition? It is. 4 times 15 will give me 60 volts. Is 60 volts 3 times higher than the voltage drop here? Because look at the relationship between the opposition. It is. 3 times 20 would give me 60. 3 times 5 would give me 15. So we have multiple ways of looking at a circuit based on the relationships. And Kirchhoff's voltage law, because that's a constant in a series circuit, we can use each one of these relationships to prove and then double check with ourselves to make sure that we're on the right path when we're looking at these relationships within a series circuit. So let's do everybody's favorite thing. Let's add a resistor. And how is that going to affect the voltage and the current everywhere else? So if I just increase, say I take a resistor right here, and again, it does not matter where I place this. I add a resistor. What is going to happen to my total resistance? It is going to increase. So if my total resistance increases, what is going to happen to current? Ohm's law said it's inversely proportional, so I will decrease my total current. If I decrease my total current, what is going to happen to the volt drops everywhere else? Look at the formula, okay? If I decrease the current, the volt drop has to decrease. You didn't change this ohmic value. So we can look at through all of that. You can also look at it as Kirchhoff's voltage law. I have another voltage to add up. So because this magnitude of my applied EMF doesn't change, the voltage drops across each other component that were existing, there has to be something removed. Why? Because I have a lower current and it has to be shared with that new component that I have added in. And it looks, we can go through each of those relationships. Depending on the size of that resistive value, the impact that it had on the circuit is going to depend. If it doubled the opposition, then I would have halved my current. There's some different relationships that we can look at there. And it helps you to plug in some numbers, make this a 5 ohm resistor, make this a 3 ohm resistor, and see how those numbers and all of those relationships hold true throughout the entire circuit. I hope this has helped. We'll see you in the next one.